Section 7.2 was about confidence intervals for population proportions, and section 7.3 is about confidence interval for the mean of a population. So when we have a random variable x that is approximately normally distributed, we looked at what happens when we take a sample of these various values to create a sample mean x bar. So when the population standard deviation is known, we know that the sample means follow a normal distribution with a mean of mu, the population mean, and a standard deviation of sigma, the population standard deviation, divided by the square root of n, the sample size. But when sigma, the population standard deviation, is not known, we use S, the population, the sample standard deviation, to estimate it. So then x bar follows a different shape called the t-distribution, or student's t-distribution. So that's what we'll be talking about here in section 7.3, the t-distribution. So the sample mean is distributed according to a t-distribution with a mean equal to the population mean, and the standard deviation is the sample standard deviation by the square root of n, n being the sample size. Let's go over some of the characteristics and properties of the t-distribution. Like the normal distribution, the t-distribution is bell-shaped. It's bell-shaped. And it is symmetric. Symmetric. The mean and mode and median are still at 0, but the standard deviation is greater than 1. And the total area under the curve is still equal to 1 or 100%. And the t-distribution has a larger standard deviation, than the standard normal. So when you look at the curves here, the one that's kind of the lower one, there would be an example of a z distribution, and the other ones are the t distributions, and they kind of look like the ones that this one is squished from the top to flatten it somewhat. So it has thicker tails and a lower peak. And here's a new concept. The t-distribution is a family of curves where the shape is determined by the so-called degrees of freedom. And we'll discuss later on where that term comes from. And the degrees of freedom is typically n minus 1, the sample size minus 1. And then as the degree of freedom increase, the curves get closer and closer to the normal distribution. So before we find t-critical values from StatCrunch or any other method, remember this is a t-distribution, so t is along this axis here, and then the area is alpha, and so that's then this point is t sub alpha would be at this point here. as T sub alpha. So the area to the right is alpha. The area to the right of T sub alpha is equal to alpha. So here are the steps. To find the T critical values, T sub alpha divided by 2, we need to know, number 1, the area and the tail, T sub alpha divided by 2, and the degrees of freedom, and that's abbreviated df, and that's simply equal to n minus 1. So alpha is 1 minus the confidence level. For example, if the confidence level is 90%, then alpha would be 1 minus 0.9 or equal to 0.1, and then alpha divided by 2 would be 0.05, where this is the area in the tail. So let's find the critical values for 90% confidence level when the sample size is 13. In other words, degrees of freedom would equal 12. And we're going to look it up in a table, the t-distribution table. And so here is an example, and you can print them out. They're available online everywhere else. So on the left side, we have the degrees of freedom, and on the right side, we have the areas and the tail. So for the degrees of freedom 13, that gives us a size 12 would be the degrees of freedom. And we want 0.05, 1/2 of 0.1, 0.05. So this would be the T critical value for sample size 13 and, and 0.05, area 0.05 in the tail, 1.782. Again, you can find these tables online or in a book, or it's in the textbook also, so you certainly have access to the information. Similarly, when we look at the next one, for 98% confidence level, when the sample size is 10, so degrees of freedom is 9. In this case, alpha would be 2% or 0.02, and alpha divided by 2, the area in the right tail would be 0.01. So let's use the tables again for this one here. So now with a degree of freedom 9, so degrees of freedom 9, and then we want 0.01 in the right tail. So there would be 2.821. I don't know how well you can see it, but it's this value here, 2.821. So that would be the T critical value, 2.821. And let's say for the 80% confidence level, when the sample size is 17, so the degrees of freedom is 16, and we know that alpha is equal to 20%. So alpha divided by 2 is equal to 10% or 0.1. So for degree of freedom of 16, that would be this row here. And for the area in the tail, 0.1. Move it up here, 0.1. So the value would be 1.337. 1.337. And for the last example, for the 99 confidence level, when the sample size is 38, so our degrees of freedom is 37. So we know that alpha is 1%, and alpha divided by 2 is 1/2 of 1% or 0.005. That's the area in the right tail. So when we look at the table, we go to row 37. So 37 would be here in this row, and we are looking for a point is this one here, 0.005. So it would be 2.715. So 2.715. 2.715. So again, you can use technology like StatCrunch or TI-34 or whatever, or use tables. Either way, you come up with the right answers if you do it correctly. And I hope that these examples help you to find the t-critical values. So for t-intervals, confidence intervals for the population mean, mu, when the standard deviation for the population is unknown, is the sample mean minus the margin of error, less than mu, the population mean, less than the sample mean, plus the margin of error, where the the margin of error, is t sub alpha divided by 2 times the square root times s divided by the square root of n. So the margin of error is t sub alpha divided by 2 times s divided by the square root of n, where s is the sample standard deviation and n is the sample size. Now, for samples that are smaller than 30, you need to do two things. Check to see if the population is approximately normally distributed, and check that there are no outliers. So let's look at an example. In a random sample of 13 American adults, the mean amount of garbage per person per day was 4.3 pounds, and the standard deviation was 0.3 pound. Assuming garbage amounts are normally distributed, construct a 90% confidence interval for mu, the average amount of garbage per person per day in the United States. So when we look at the requirement checks, is n greater than or equal to 30? No, it is not. However, we are told that the garbage amounts are normally distributed. So normally distributed. So that'll work. Normally distributed. And are there any outliers? No, there are no outliers. So the second requirement is satisfied also. So no outliers. No outliers. Okay, so we have a 90% confidence level. So that means that alpha is equal to 10%, or 0.1. So alpha divided by 2 is equal to 0.05. And the degrees of freedom is equal to 13 minus 1, n minus 1, or equal to 12. So with this information, whether we use the tables or technology, t sub alpha divided by 2 is equal to 1.782. So then our margin of error, t sub alpha divided by 2 times s divided by the square root of n. And what was s? S was equal to 0.3. The sample standard deviation was 0.3 pounds. So s was equal to 0.3. So then our margin of error is 1.782 for t sub alpha times 0.3 divided by the square root of 13, and that is equal to 0.1483 pounds. So that's our margin of error here. And so at the 90% confidence, we can say that x, the mean, sample mean, plus or minus the margin of error, equals 4.3 plus or minus 0.1483. So let me rewrite this here. So x, the sample mean, plus or minus the margin of error, equals 4.3 plus or minus 0.1483. Or we can say that the population mean is between 4.4483 and 4.1517. So we can say with 90% confidence we can predict the mean garbage per person per day is between 4.15 and 4.45 per pounds, with a margin of error of 1.15 pounds. So again, to repeat the sentence, with 90% confidence we can predict that the mean garbage per person per day in the US is between 4.15 and 4.45 pounds, with a margin of error of plus or minus 0.15 pounds. Let's look at another example. A random sample of 35 airfare prices in dollars for a one-way ticket from Atlanta to Chicago. Find a 95% confidence interval estimate for the population mean, mu, the mean price for all one-way flights from Atlanta to Chicago. So the first thing we need to do here with this 35 sample prices, we need to find the sample mean, and whether you add everything up manually and divide by 35, or if you use, Excel, whatever it is, but the sample mean x bar is equal to 101.77, and the sample standard deviation is, S, of course, equals 6.691. As far as the requirement checks is concerned, since n is greater than or equal to 30, so we are good. So when we use technology or do it explicitly manually, we will come up with these results. When you use technology, the confidence interval will go from 99.47, less than the mean of all the flights between Chicago and Atlanta, and 104.07. If you want to do it manually, since alpha is equal to 1 minus 0.95, it is 0.05, so then alpha divided by 2 is 0.0025, and then the t sub alpha divided by 2 is equal to 2.032 for a degree of freedom of 34. So degrees of freedom is 34. 35 minus 1. So that's our t critical value. So then our margin of error, is 2.032 times the sample standard deviation, which was 6.691, divided by the square root of 35. And that's equal to 2.30. So then our confidence interval will be 101.77 plus or minus our margin of error of 2.30, and that'll give us this confidence interval at the 95% level. So we can summarize our results in a sentence where we can say with 95% confidence we can predict the mean price for all one-way flights from Atlanta to Chicago is between $99.47 and $104.07 with a margin of error of plus or minus $2.30. In another example, we are considering bacteria found in milk. The pasteurization process reduces the amount of bacteria found in dairy products such as milk. The following data represents the counts of bacteria in pasteurized milk in cubic or CFU per milliliter for a random sample of 12 pasteurized glasses of milk. Construct a 95% confidence interval for the mean bacteria count. CFU, colony forming units per milliliter. So requirement checks, we need to do that since n is less than 30. And when we use different methods, we find that it is normal, approximately normally distributed. Turns out that works out. And also there are no outliers. I'm going to skip over this step here in detail because it's a little bit more complicated. From the given information, with a confidence level of 95%, that means that alpha is 1 minus 0.95 or 0.05 or 5%. Then alpha divided by 2 is 0.025. Degrees of freedom is 11. And it turns out the mean is 6.41 and the sample standard deviation is 4.55. So now when we look up the T sub alpha divided by 2 critical value, if we look at the table, we go to 11 degrees of freedom and we go to 0.025, and so T sub alpha divided by 2 is 2.201. So T sub alpha divided by 2 is 2.201. Then our margin of error is T sub alpha divided by 2, 2.201, times the sample standard deviation of 4.55 divided by the square root of n, or 12, and that gives us a margin of error of 2.89. So then our confidence interval is equal to the margin of error. It is equal to the mean, the sample mean. So with our margin of error of 2.89, then our confidence interval is the sample mean plus or minus the margin of error, so it's 6.41 plus or minus 2.89, and that'll give us our confidence interval for the population mean between 3.519 and 9.301. So we can summarize our result as follows. With 95% confidence, we can predict the mean bacteria count in a glass of pasteurized milk is between 3.52 and 9.30 CFU per milliliter, with a margin of error of plus or minus 2.89 CFU per milliliter. The next example explains how confidence intervals can be used. It's about space travel. The following data represents the red blood cell mass in milliliters of 15 rats in a flight group and the 15 rats in a control group on the ground. The red blood cell mass was measured immediately after the flight group returned from space on the Space Lab Sciences 2 and compute a 95% confidence interval for the population mean mass of red blood cells in rats that traveled to space. So as we do the requirement checks, it turns out everything checks. They're approximately normally distributed and there are no outliers. When you compute the confidence intervals, the 95% confidence intervals for each group, then you find for the flight group it's between 7.3588 and 8.4492, and for the control group between 7.9341 and 9.3726. So when we graph the intervals approximately, this is not exact, but approximately, you notice that the intervals overlap. And since the intervals overlap, a case can be made that the difference in the red blood cell mass for the flight group compared to the control group, we could have the same mean. That is certainly possible since the confidence intervals overlap. So the population means of the two groups could be equal. So when we compare the two confidence intervals, we find they overlap. So there is no clear difference in the mean red blood cell mass in rats that go into space and those that don't. So and here's the amount of overlap that you see here. Finding the correct sample size for a given confidence level is just as important as it was before. And here's the equation. So n, the sample size, would be T sub alpha divided by 2 times the sample standard deviation divided by the margin of error, and the whole quantity is squared. And that is derived from the formula that we had for the margin of error, T sub alpha divided by 2 times the standard deviation divided by the square root of n. So when we solve this equation for n, we begin by squaring both sides. Then this will be our result for the sample size for a given margin of error. So where n, of course, is always a whole number. So in other words, when we calculate n, and there's typically a decimal part to that, we always increase that to the next whole number. Okay, we always increase it. Now we know when the standard deviation of the populations are known, we use S, which is the sample standard deviation. And as n increases, so let's summarize this. When sigma, the population standard deviations are known, we use S, the sample standard deviation. Now, remember, as n increases, the t distributions approach the standard normal z distribution. Now, since we don't have n yet, we don't have the degree of freedom either, so we can use z sub alpha divided by 2 in place of t sub alpha divided by 2. So that's why we have the second formula here. Summarizing the information we have, alpha is 1 minus 0.95 since the confidence level is 95%. So that means alpha is equal to 0.05, and then z sub alpha divided by 2 is 1.96. We're given that S, the sample standard deviation, is 25, and that E, the margin of error, is $5 in this case. So N is then equal to Z sub alpha divided by 2 times S, all divided by E, quantity squared. So that would be 1.96 times 25 divided by 5, quantity squared, and that's 96.04. So we need to sample 97 flights. Let's look at the next example. How large a sample would be required to estimate the mean hours spent by CRC students on homework per week within half an hour with 99% confidence. So here we're supposed to use the standard deviation of the population as 5 hours. Well, as before, N is equal to Z sub alpha divided by 2. In this case we use sigma divided by E, the margin of error, the whole quantity squared. So in this question, in this exercise, again we said N equal to Z sub alpha divided by 2 times sigma, the standard deviation of the population, divided by the margin of error squared. And so we know that Z sub alpha divided by 2 for alpha being 0.01 is 2.576 times 5, the standard deviation, divided by 0.5, and that's 663.57, etc. So we need to round it up to 664. So the answer is we would need to sample 664 CRC students. So these two examples showed you specifically how to compute the sample size to achieve a certain, a given margin of error. So putting it all together, when to use which method. So the main question that determines the method we're going to use is, what are we trying to estimate? What are we trying to estimate? To estimate the population mean or the population proportion. So when estimating a population proportion, we need to check if n times p is greater than 5 and n times q is greater than 5, and that the sample size is less than 0.05 times the population size. So to estimate the population proportion, p, we use p hat, the sample proportion, plus or minus z sub alpha divided by 2 times the square root of p hat times q hat divided by n. When estimating a population mean, the first question is the sample large? So if n, the sample size, is greater than or equal to 30, we just go ahead with the confidence interval. If n is less than 30, we need to do some checking to see if, check for outliers. And we can use a box plot, outliers, and check for normality. Check for normality. We haven't really discussed how to do that, but there are several methods involved, so we're not going to go into any details about that. So there are 3 formulas for sample sizes. So the 2 versions for the sample size formula when estimating population proportion is when we have a preliminary estimate for p hat, the sample proportion, then our sample size n is equal to z sub alpha divided by 2 squared times p hat q hat divided by e, the margin of error, squared. And when we don't have a preliminary estimate for p hat, for the sample proportion, then we use the following. N is equal to z sub alpha divided by 2 squared times 0.25 divided by e squared. And the sample size formula when estimating a mean is equal to n equals z sub alpha divided by 2 times sample standard deviation divided by the margin of error, quantity squared. And of course, whatever n is, if there's a fraction of a decimal, always round up to the nearest integer. Round up to the next whole number. And that applies to all three formulas. So that's true for this one, and for that one, and for this one. So I wrote the expressions for estimating a population mean when we have the proportion, the sample proportion, and the margin of error. And here's how we compute the population mean, the estimated population mean between the sample mean minus the margin of error and the sample mean plus the margin of error. So this concludes section 7.3.